Alright, question 1a. Find the kinetic energy of a 9 kilogram baby who is crawling at 0.4 meters per second. Alright, so for this we just need to know the equation for kinetic energy. It's right here. So kinetic energy is equal to 1/2 mass velocity squared. So the mass is 9 kilograms, the velocity is 0.4 squared. And that's it, we're just typing all of this in to our calculator. And I get 0.72, and the units for energy is joules. So as long as you're using SI units for everything, so my mass is in kilograms, my velocity is in meters per second, then the units will work out to be in joules. All right, so those are the SI units for energy. All right, 1b. If the ground is defined as 0 height, what is the gravitational potential energy of a 60 kilogram lady who is about to bungee jump, who is about to bungee jump off the edge of a 35-meter tall bridge? Okay, so gravitational potential energy is up here, the equation. So UG, U for potential, G for gravitational. Okay, so gravitational potential energy is equal to m mass, G, which is 9.8, h, which is the height. So the height is always from some reference position. And in this case, they said the reference position is the ground because it's defined as a 0 height. Okay, so the ground is at 0 height. She is now at the edge of a 35-meter tall building, so that is her height. So the mass of the lady is 60 kilograms, G is 9.8, and H is 35.0 meters. Okay, so then we can just type this into the, and I get 20,580. The units for energy is in joules. Okay, but when we look at significant figures, there was only one significant figure here, so our answer should be rounded to only one. So it should just be UG is equal to 20,000 joules. Okay, one significant digits, those other zeros are not significant. All right, 1C, elastic potential energy. So they tell us that elastic potential energy stored in your tendons can contribute up to 35% of your energy needs when running. Sports scientists find that the knee extensor tendons in sprinters stretch 41 millimeters, while those of non-athletes stretch only 33 millimeters. The spring constant of the tendon is the same for both groups, 33 newtons per millimeter. What is the difference in the maximum stored energy between the sprinters and the non-athletes? Okay, so we have to do this twice, once for sprinters, once for non-athletes. All right, so elastic potential energy, the equation is over here. Again, U is for potential, E is elastic. So elastic potential energy is equal to 1/2 K, which is the spring constant, delta X squared. Now the delta X is the amount that the spring has either been stretched or compressed compared to its original equilibrium position. So for the sprinter, it says it can stretch 41 millimeters. So then that would be the delta X for the sprinter. Now remember, everything has to be in SI units, so we need to change that 41 millimeters into meters. So that would be the same as just dividing it by 1,000, so we'd get 0.041 meters. So that's my delta X for the sprinters. And then for non-athletes, it's 33 millimeters, so the delta X for non-athletes, I'll just say NA for non-athletes, is equal to 0.033 meters. Okay, everything has to be in SI units. Same with this over here, which is the K, the spring constant. So K is equal to 33 newtons per millimeter, but we want it to be in SI units, which would be newtons per meter. So we got to get rid of millimeters, so we'll put it on top and change it into meters. And 1,000 millimeters is the same as 1 meter. So the millimeters cancel off, and we get 33 times 1,000, 33,000 newtons per meter. Okay, so for sprinters, we're going to plug in 1/2 K is 33,000. Delta X for sprinters was 0.041 squared. And when we do this for non-athletes, the equation is still the same. My K is the same for both groups, so 33,000. But my delta X for the non-athletes is 0.033 squared. And then I'm just going to type both of these into my calculator. So for my sprinters, I get 27.7. Let's look at my significant figures. I have 41 millimeters here, 33 millimeters, 33 newtons per millimeter. So all of these are two significant figures. So I had 27.7. I'm going to round up to 28 joules. And then for my non-athletes, I'm going to type everything into my calculator. And I get 17.9685. So I'm going to round it to two significant figures. I get 18 joules. So the question says, what is the difference in the maximum stored energy between the sprinters and the non-sprinters? So the sprinters are able to store 28 joules of energy in their tendons, and the non-athletes are only able to store 18 joules. So therefore, the difference between those two numbers means when you subtract those two numbers, what do you get? The difference in the maximum stored energy is 28 minus 18, so 10 joules. There we go. All right, so hope that makes sense. So that was an example of the three different types of energy that we're going to be discussing in this course: kinetic energy, gravitational potential energy, and spring energy. Okay, the one thing for spring energy that people tend to get confused on or to mix up is that the delta X in the equation needs to be the distance that the spring was either stretched or compressed. Either way, it's the same value. The same equation that you're using. It doesn't matter if you put in a negative because you can see it's being squared anyways, so that doesn't matter. So it's not the length of the spring, it's the distance it was stretched or compressed. So if a spring was initially 5 meters long and now you stretch it and it's now 7 meters long, then the delta X would be 2 meters because it got stretched an additional 2 meters from its initial equilibrium position. Okay, I hope that helps. Thanks for watching.